The significant figures of a number are digits that carry meaning contributing to its measurement resolution. This includes all digits except all leading zeros, trailing zeros when they are merely placeholders to indicate the scale of the number, and spurious digits introduced, for example, by calculations carried out to greater precision than that of the original data, or measurements reported to a greater precision than the equipment supports. Significance arithmetic are approximate rules for roughly maintaining significance throughout her computation. The more sophisticated scientific rules are known as propagation of uncertainty. Numbers are often rounded to avoid reporting insignificant figures. For example, it would create false precision to express a measurement as 12.3450 kilograms if the scales only measured to the nearest gram and gave a reading of 12.345 kilograms. Numbers can also be rounded merely for simplicity rather than to indicate a given precision of measurement. For example, to make them faster to pronounce in news broadcasts. Identifying significant figures. Concise rules: all non-zero digits are significant. Zeros between non-zero digits are significant. Leading zeros are never significant. In a number with a decimal point, trailing zeros, those to the right of the last non-zero digit, are significant. In a number without a decimal point, trailing zeros may or may not be significant. More information through additional graphical symbols or explicit information on errors is needed to clarify the significance of trailing zeros. Significant figures rules explained specifically. The rules for identifying significant figures when writing or interpreting numbers are as follows. All non-zero digits are considered significant. For example, 91 has two significant figures, while 123.45 has five significant figures. Zeros appearing anywhere between two non-zero digits are significant. Example: 101.1203 has seven significant figures: 1, 0, 1, 1, 2, 0 and 3. Leading zeros are not significant. For example, 0.00052 has two significant figures: 5 and 2. Trailing zeros in a number containing a decimal point are significant. For example, 12.2300 has six significant figures: 1, 2, 2, 3, 0 and 0. The number 0.000122300 still has only six significant figures. In addition, 120.00 has five significant figures since it has three trailing zeros. This convention clarifies the precision of such numbers. For example, if a measurement precise to 4 decimal places is given as 12.23, then it might be understood that only 2 decimal places of precision are available. Stating the result as 12.2300 makes clear that it is precise to 4 decimal places. The significance of trailing zeros in a number not containing a decimal point can be ambiguous. For example, it may not always be clear if a number like 1300 is precise to the nearest unit or if it is only shown to the nearest hundred due to rounding or uncertainty. Many conventions exist to address this issue. An overline, sometimes also called an overbar, or less accurately, a vinculum or a macron, may be placed over the last significant figure. Any trailing zeros following this are insignificant. For example, 1300 has 3 significant figures. Less often, using a closely related convention, the last significant figure of a number may be underlined. For example, 2000 has 2 significant figures. A decimal point may be placed after the number. For example, 100 indicates specifically that 3 significant figures are meant. In the combination of a number and a unit of measurement, the ambiguity can be avoided by choosing a suitable unit prefix. For example, the number of significant figures in a mass specified as 1,300 grams is ambiguous, while in a mass of 13 hectograms or 1.3 kilograms it is not. However, these conventions are not universally used. and it is often necessary to determine from context whether such trailing zeros are intended to be significant. If all else fails, the level of rounding can be specified explicitly. The abbreviation SF is sometimes used, for example, 20,000 to 2SF, or 20,000. Alternatively, the uncertainty can be stated separately and explicitly with a plus-minus sign, as in 20,000 plus or minus 1%, so that significant figures rules do not apply. This also allows specifying a precision in between powers of 10. Scientific notation. In most cases, the same rules apply to numbers expressed in scientific notation. However, in the normalized form of that notation, placeholder leading and trailing digits do not occur, so all digits are significant. For example, 0.0012 becomes 6996120000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 becomes 699712230000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 that the significance of trailing zeros is eliminated. For example, 70031300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 103, while 70031300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 because times 103. The part of the representation that contains the significant figures is known as the significand or mantissa. Rounding and decimal places. The basic concept of significant figures is often used in connection with rounding. Rounding to significant figures is a more general-purpose technique than rounding to decimal places, since it handles numbers of different scales in a uniform way. For example, the population of a city might only be known to the nearest thousand and be stated as 52,000, while the population of a country might only be known to the nearest million and be stated as 52 million. The former might be in error by hundreds, and the latter might be in error by hundreds of thousands, but both have two significant figures. This reflects the fact that the significance of the error is the same in both cases. To round to insignificant figures. If the first non-significant figure is a 5 followed by other non-zero digits, round up the last significant figure. For example, 1.2459 as the result of a calculation or measurement that only allows for 3 significant figures should be written 1.25. If the first non-significant figure is a 5 not followed by any other digits or followed only by zeros, rounding requires a tie-breaking rule. For example, to round 1.25 to 2 significant figures, round half up, rounds up to 1.3. This is the default rounding method implied in many disciplines if not specified. Round half to even, which rounds to the nearest even number, rounds down to 1.2 in this case. The same strategy applied to 1.35 would instead round up to 1.4. Replace non-significant figures in front of the decimal by zeros. In financial calculations, a number is often rounded to a given number of places. Rounding to a fixed number of decimal places in this way is an orthographic convention that does not maintain significance, and may either lose information or create false precision. As an illustration, the decimal quantity 12.345 can be expressed with various numbers of significant digits or decimal places. If insufficient precision is available, then the number is rounded in some manner to fit the available precision. The following table shows the results for various total precisions in decimal places rounded to the nearest value using the round to even method. The representation of a positive number x to a precision of p significant digits has a numerical value that is given by the formula round 10n, where n equals floor plus 1 minus p. For negative numbers, the formula can be used on the absolute value. For 0, no transformation is necessary. Note that the result may need to be written with one of the above conventions explained in the section identifying significant figures to indicate the actual number of significant digits if the result includes, for example, trailing significant zeros. Arithmetic. As there are rules for determining the number of significant figures in directly measured quantities, there are rules for determining the number of significant figures in quantities calculated from these measured quantities. Only measured quantities figure into the determination of the number of significant figures in calculated quantities. Exact mathematical quantities like the pi and the formula for the area of a circle with radius r. Pi r2 has no effect on the number of significant figures in the final calculated area. Similarly, the 1/2 in the formula for the kinetic energy of a mass m with velocity v, 1/2 mv2, has no bearing on the number of significant figures in the final calculated kinetic energy. The constants pi and 1/2 are considered to have an infinite number of significant figures. For quantities created from measured quantities by multiplication and division, the calculated result should have as many significant figures as the measured number with the least number of significant figures. For example, 1.234 times 2.0 equals 2.468, 2.5, with only 2 significant figures. The first factor has 4 significant figures and the second has 2 significant figures. The factor with the least number of significant figures is the second one with only 2. So the final calculated result should also have a total of 2 significant figures. For quantities created from measured quantities by addition and subtraction, the last significant decimal place in the calculated result should be the same as the leftmost or largest decimal place of the last significant figure out of all the measured quantities in the terms of the sum. For example, 100.0 plus 1.234 equals 101.234, 101.2 with the last significant figure in the tenths place. The first term has its last significant figure in the tenths place and the second term has its last significant figure in the thousandths place. The leftmost of the decimal places of the last significant figure out of all the terms of the sum is the tenths place from the first term, so the calculated result should also have its last significant figure in the tenths place. The rules for calculating significant figures for multiplication and division are opposite to the rules for addition and subtraction. For multiplication and division, only the total number of significant figures in each of the factors matter. The decimal place of the last significant figure in each factor is irrelevant. For addition and subtraction, only the decimal place of the last significant figure in each of the terms matters. The total number of significant figures in each term is irrelevant. In a base 10 logarithm of a normalized number, the result should be rounded to the number of significant figures in the normalized number. For example, log 10 equals log 10 plus log 10 4 plus 0.4771212547 should be rounded to 4.4771. When taking anti-logarithms, the resulting number should have as many significant figures as the mantissa in the logarithm. When performing a calculation, do not follow these guidelines for intermediate results. Keep as many digits as is practical until the end of calculation to avoid cumulative rounding errors. Estimating tenths. When using a ruler, initially use the smallest mark as the first estimated digit. For example, if a ruler's smallest mark is cm, and 4.5 centimeters is read, it is 4.5 or 4.4 4.6 centimeters. It is possible that the overall length of a ruler may not be accurate to the degree of the smallest mark, and the marks may be imperfectly spaced within each unit. However, assuming a normal good quality ruler, it should be possible to estimate tenths between the nearest two marks to achieve an extra decimal place of accuracy. Failing to do this adds the error in reading the ruler to any error in the calibration of the ruler. Estimation. When estimating the proportion of individuals carrying some particular characteristic in a population, from a random sample of that population, the number of significant figures should not exceed the maximum precision allowed by that sample size. The correct number of significant figures is given by the order of magnitude of sample size. This can be found by taking the base 10 logarithm of sample size and rounding to the nearest integer. For example, in a poll of 120 randomly chosen viewers of a regularly visited web page, we find that 10 people disagree with a proposition on that web page. The order of magnitude of our sample size is log 10 equals 2.079181240, which rounds to 2. Our estimated proportion of people who disagree with the proposition is therefore 0.083, or 8.3%, with two significant figures. This is because in different samples of 120 people from this population, our estimate would vary in units of 1/120th, and any additional figures would misrepresent the size of our sample by giving spurious precision. To interpret our estimate of the number of viewers who disagree with the proposition, we should then calculate some measure of our confidence in this estimate. Relationship to accuracy and precision in measurement. Traditionally, in various technical fields, accuracy refers to the closeness of a given measurement to its true value. Precision refers to the stability of that measurement when repeated many times. Hoping to reflect the way the term accuracy is actually used in the scientific community, there is a more recent standard, ISO 5725, which keeps the same definition of precision but defines the term trueness as the closeness of a given measurement to its true value, and uses the term accuracy as the combination of trueness and precision. In either case, the number of significant figures roughly corresponds to precision, not to either use of the word accuracy or to the newer concept of trueness. In computing, computer representations of floating point numbers typically use a form of rounding to significant figures, but with binary numbers, the number of correct significant figures is closely related to the notion of relative error.